All right, hello. So this is section 7.4, trigonometric identities. It's actually one of my favorite sections, so I hope you guys enjoy it and see that. Basically, we're just doing some trig puzzles. That's what's coming down to. So in our previous sections, with identity, we learned what sine squared plus cosine squared theta equals 1. We developed that. What makes this an identity is that just like every person, his or her identity, we say that equation is an identity if it maintains its value for every value of the input. So no matter what I put into this equation, it's going to always equal 1. That's what makes it an identity. It doesn't change who it is. So if we look here, we're just going to confirm that the identity, Pythagorean identity, is true for any theta. So for example, if you typed for theta, make sure your calculator is in degree mode. But if I put theta equals 35 degrees into the Pythagorean identity, do I get 1? And if I put theta in as 5 pi over 3 into the identity, do I get 1? And the answer is yes. Please be mindful of when you're squaring. Notice how I had to put parentheses around my sign and then squared. That's the only way you can represent sine squared in the calculator. So make sure you're putting the parenthesis in the beginning, the parenthesis at the end, and then your square. And that's how you would input sine squared or cosine squared. Okay. Um, yeah. So what happens? So if I was to look at this graph, the sine squared theta plus cosine squared theta, and my output is always going to be 1. That means no matter what, y equals 1. That means that my graph is going to look like a horizontal line. Because no matter what my input is, my output is always going to be 1. Y equals 1. Okay. So the difference between an identity and an equation. Well, an equation that is not an identity is called a conditional equation, and that means that it's only true for given values. So like if you look at this equation, we have 2 times x minus 3 equals 5. Well, this is only true at x equals 11 halves. Or if we had sine x is only true if x is an integer of the multiple of pi. So it just depends on whether it's true for all or true for some. If it's true for every single input, then it's an identity. If it's true for specific inputs, then it's a conditional equation, which is what we just call an equation. So to summarize that, two functions f and g are said to be identically equal if f of x equals g of x. That means your outputs equal each other for every value of x for which both functions are defined. Such an equation is referred to as an identity. An equation that is not an identity is called a conditional equation, which is what we've been working with since pre-algebra. Okay. All right. So our basic trig identities, these are going to be our puzzle pieces, so to speak, that we're going to use to simplify or establish identities. So these are going to be our puzzle pieces that we use. So if we're remembering our quotient identities, our quotient rule for trig. So quotient identity, we have sine theta over cosine theta. And cotangent theta is cosine theta over sine theta. You could also write them in terms of secant and cosecant. If need be, just know how to work backwards to get here. But ideally, we want to focus on things in terms of sine and cosine, and occasionally tangent. Our reciprocal identities, well, sine theta is 1 over, cosecant theta is 1 over sine theta. It's a weird I, but you see it. Secant theta is 1 over cosine theta, and cotangent theta is 1 over tan theta. And of course, through some algebra, you can always rewrite them as sine theta equals 1 over cosecant theta, cosine theta equals such and such. Next, we have our trig identities. And so with our trig identities, we have sine squared theta plus cosine squared theta, and that's going to equal 1. And then we have our tan squared theta plus 1 equals secant squared theta. And then we have cotangent, 1 plus cotangent squared theta equals cosecant squared theta. And now we have our even odd identities. So on our even odd identities, if I have the sign of a negative theta, it's equal to negative sign of the positive theta. If I have the cosecant of a negative theta, it's equal to the negative cosecant of the positive theta. If I have cosine of a negative theta, it's just equal to the cosine of the positive theta. If I have the secant of a negative theta, it's equal to the secant of the positive theta. And if I have tan negative theta, it's equal to negative tan of the positive theta. And if I have cotangent of a negative theta, it's equal to the negative cotangent of theta. All right, algebra things that we need to recall. So some of the basic algebra techniques you need to remember is, one, how to rewrite trig expressions in terms of sine and cosine. So just using those identities that we just talked about. Also multiplying the numerator and denominator of a ratio by a well-chosen one. So manipulating your graph by multiplying by what I like to call a fancy one, okay? Because when you multiply by 1, it doesn't change the value. It changes how it looks, but it doesn't change the value. Writing sums of trig ratios as a single ratio, and factoring. So these are some of the skills that we're going to have to utilize. All right, so let's choose our first example, and we're talking about that well-chosen one. Again, your fancy one. Oh, my highlighter got a little happy. So your fancy one that's going to make this work. So if I have sine theta over 1 plus cosine theta, what we want to try to do is use this, change this to something that we are factorable, or make it look like a property, not a property, one of our identities. And so we can use its conjugate. And if we remember, conjugate just means that instead of having 1 plus cosine theta, we're going to have 1 minus cosine theta. And that's what we're going to use to make our well-chosen one. And it's a well-chosen one because you're going to multiply the numerator and the denominator by that value. Okay, so if I multiply, I end up with sine theta times 1 minus cosine of theta over 1 minus cosine squared theta. And we can we should be able to easily jump here because this is dots, difference of two squares. And so we have difference of two squares factored. This is what it looks like. So kind of jump straight to that using those factoring skills. All right, after I have that, I'm going to look at this 1 minus cosine squared. Well, 1 minus cosine squared should make you think of your Pythagorean identity of, I keep clicking the button that keeps dragging my pen. I apologize. So we have sine squared plus cosine squared equals 1, right? So if I have sine squared plus cosine squared equals 1, and I subtracted cosine squared, all I'm left with is sine squared. So I know that 1 minus cosine squared is sine squared theta. And in my numerator, I have sine theta, 1 minus cosine theta. Okay, so if you look here, we have a sine in the numerator and two signs in the denominator. So I can eliminate 1, and I'm left with 1 minus cosine theta over sine theta. Okay, when you are dividing by a monomial, so when I'm dividing by a monomial, which is one term in the denominator, I can actually split this up. So if I have this is the same thing as this being split up into 1 over sine theta minus cosine theta over sine theta. 1 over sine theta, this right here, going back and looking at our identities, this is a reciprocal function. And this guy right here is a ratio function. So 1 over sine theta is equal to cosecant theta. And cosine theta over sine theta is equal to cotangent theta. So this is what this reduces down to, or simplifies to. Cosine theta minus cotangent theta. All right, so I hope that you're getting your feet wet using the identities as a puzzle piece and navigating through it. Let's keep going. All right, another method of simplifying trig expressions is to rewrite an expression over a common denominator. So we have 1 over 1 minus sine theta plus 1 over 1 plus sine theta. And by first finding the LCD. So our common denominator here, our least common denominator here would be simply multiplying the two denominators together. So we have 1 minus sine theta times 1 plus sine theta. And remember how we talked about difference of two squares? Well, this is difference of two squares factored. So our LCD is actually 1 minus sine squared theta. So that's what our one denominator ultimately is going to be, right? So when I come down here, I ask myself, well, how can 1 minus sine theta become 1 minus sine squared theta? Well, that's by multiplying by 1 plus sine theta. What I do to the denominator, I need to do to the numerator. How can 1 plus sine theta become 1 minus sine squared theta? Well, I have to multiply by 1 minus sine theta. What I do to the denominator, I do to the numerator. And so once I multiply, I now end up with 1 times 1 plus sine theta is just 1 plus sine theta. And my denominator is now 1 minus sine squared theta plus 1 minus sine theta over 1 plus sine squared theta. Now that I have a common denominator, that means I can combine my numerator and my denominator. So I have 1 plus sine theta plus 1 minus sine theta all over 1 minus sine squared theta. So at this point, my signs cancel out because I have a positive and a negative. And 1 minus sine squared theta can become cosine squared theta because it's a Pythagorean identity. So in the end, I'm left with 1 plus 1, which is 2, over cosine squared theta. And there we go. So just recapping what we did, we used difference of two squares. We went through and got 1 minus sine squared as our LCD. We multiplied to create our LCD, and then we combined our two ratios. We simplified our two ratios, used Pythagorean identity, came to our new conclusion. All right, so the next one that we're going to talk about is using factoring. Okay, so taking some of those factoring skills, we've kind of been talking about them already. So in your numerator here, we're using dots, difference of two squares. And our denominator, we're just using GCF, greatest common factor, right? So dots tells me that this becomes 1 minus cosine V times 1 plus cosine V. And then here our GCF is sine, so we're going to factor out sine V, and we're left with 1 plus cosine V. All right, so after we've done that, now we can eliminate. Well, I have a 1 plus cosine V in the denominator and in the numerator. So I eliminate and I'm left with 1 minus cosine V over sine V. Okay, we talked about when this happens, that means that you have a monomial in the denominator. So you actually are working with two separate problems. So I have 1 over sine V minus cosine V over sine V. 1 over sine V is cosecant V. Cosine over sine V is cotangent V. And so that is what this simplifies to. Ta-da! See, it's just a puzzle. And you're going through the puzzle and you're using all that you know, which puzzle piece is going to help you get to the end. So here we use reciprocal. And here we used ratio. And we ended up with cosecant V minus cotangent V. All right. So this is establishing identities. When you're establishing identities, you're just trying to prove that this is true by showing all your work to prove that it's true. So what you want to do is begin on the side that is the most complicated, okay? And you want to put everything in terms of sine and cosine when possible, and just use our basic identities that we wrote down to simplify. So we're going to start on this side, starting here, and this is our goal. So notice how it says secant theta, secant theta, secant theta. And we want to prove, and our final answer should be secant theta, okay? So we'll put everything in terms of sine and cosine. So if I want to put everything in terms of sine and cosine, the first thing I'm going to do here is distribute, right? So when I distribute, I'm going to end up with, I think I have enough room, sine. Is it okay if I hope it's okay with you guys if I don't write the theta all the way through? I will put it back in the end, but for me, it typically gets in my way. So I do not write it all the way through. I write it in the very end. You can do if you choose to. So we have sine times cotangent because I distribute, and we have sine times tangent. Okay, then I'm going to put cotangent and tangent in terms of sine and cosine. Well, cotangent is the same thing as cosine over sine. Tangent is the same thing as sine over cosine. And now I'm going to write this as a 1 ratio. So remember how we talked about LCD or chopsticks in the bowl, same concept. So chopstick, sine times sine is, wait, what am I talking about? We're not there yet. Just multiplying, silly girl. So we're just multiplying. Sine times cosine is sine times cosine. 1 times sine is sine. Sine times sine is sine squared. 1 times cosine is cosine. All right, and now we're at we want to combine them. So if I want to be able to combine them, that means I'm going to have to multiply by a LCD in order for that to happen. So my LCD here would be sine times cosine, correct? Sorry, forgot my elimination. So I have a sine in the numerator and a sine in the denominator. So I'm just now left with, what am I left with? Cosine. And sine squared over cosine. All right, well, in order to add them, I need to have a common denominator. So I'm going to have to multiply this one by cosine, so that I'll have a common denominator. And so cosine times cosine over 1 times cosine over cosine is going to give me cosine squared over cosine. And this gives me sine squared over cosine. And now they can be combined. So cosine squared plus sine squared equals 1. And my denominator is going to stay the same, which is cosine. And so 1 over cosine theta. Well, that is a reciprocal identity. And that gives me all the way down to secant theta. Proven. Puzzle completed. Okay, so let's recap what we did. So the first thing we did was we distribute. So we went through our distribution. After distribution, we then rewrote everything in terms of, so step 1, we distribute. Step 2, we rewrote everything in terms of sine and cosine. So cotangent became cosine over sine, which is a ratio. Tan became sine over cosine, which is the other ratio identity. Okay, then we multiply it, so we simplify and eliminate it. There's a sine in the numerator and a sine in the denominator, so sine got canceled. Sine times sine made sine squared, and we were left with cosine. So that was step 3. We multiply, we simplified. And then step 4 over here, we found an LCD and combined. Step 5 here, we did a little bit more simple. We used the Pythagorean identity to simplify. This is the Pythagorean identity. Step 6, we use reciprocal identity, 1 over cosine theta, and that led us to secant theta, and we proved it. Bam, we got it. All right, so again, you want to choose the side that seems the most complicated. Well, for me, anytime there's a ratio, that seems like the more complicated side. So we're going to start on the right side, and we want to prove this is our end goal. This is our goal, that these are equal, okay? We're going to establish this identity. So we're going to multiply by the conjugate of the denominator, and my conjugate is 1 minus cosine theta. After we multiply by the conjugate, we're now left with sine times 1 minus cosine over 1 minus cosine squared. From here, we know that 1 minus cosine, that's a Pythagorean identity. And so we have sine times 1 minus cosine over sine squared. Now I have a sine in the numerator and a sine in the denominator. So I can eliminate one of the signs, and we're left with 1 minus cosine over sine. Remember how we talked about when you have a monomial? That means it splits into two. It can be split into two separate terms. So we have 1 over sine minus cosine over sine. And 1 over sine is cosecant theta. And cosine over sine is cotangent theta. And so wham, bam, there's our established identity. We ended up with our goal. All right, here's another one. Again, ratio, complicated. So this one is our goal. So we have sine squared theta minus tan theta over cosecant squared theta minus cotangent theta. There's a couple ways to start here, but the main way we can start here is by putting everything in terms of sine and cosine. So tan and cotangent, we're going to transform. I'm going to need a little more space, so I'm going to start over here. So we have sine squared minus sine over cosine. That's what tangent became. All over cosine squared minus cosine over sine. So that's the first thing we needed. Okay, after we've done that, we're now going to turn our denominator and numerator of this ratio into single ratios. So in order to do that, you can either chopstick it, LCD it, however you want to think about it. I'm just going to chopstick real quick. So sine squared times cosine is sine squared cosine minus 1 times sine is sine all over 1 times cosine, which is cosine, all over my big denominator. Let me make it, there's the main denominator bar, fraction bar. And we're going to do the denominator, and we have cosine squared times sine is cosine squared times sine minus 1 times cosine is cosine all over 1 times sine is sine. So here's my big fraction. And now I'm going to go through the process of turning this into one fraction. So in order to turn it into one fraction, I'm going to have to keep, change, and flip. So keeping and changing and flipping. So we have sine squared cosine minus sine all over cosine times, and I'm going to reciprocate this, sine over cosine squared cosine. I just lost where was that? Cosine sine minus cosine. All right, so now we're here. We probably should have factored at some point. Well, we're going to factor now. So I'm going to factor. So if I was to factor this guy, this is GCF, so it can become sine is my factor, and I'm left with cosine times sine minus 1. I can factor this one, and I take out a cosine, and I'm left with cosine times sine minus 1. So now everything's factored, and now I can eliminate. So I had this cosine, sine minus 1, this cosine, sine minus 1 are eliminated, and I'm left with sine times sine, which is sine squared, and I'm left with cosine times cosine, which is cosine squared, and by ratio identity, sine squared over cosine squared equals tan squared theta. Goal made. All right. So, class announcements. Please use the remainder of the class time to take your exit ticket or prepare. Remember on your exit ticket, if you've been taking your notes throughout the week, you may use those. So you're using your 7-1 and your 7-2 notes is what your exit ticket is over. You have only 15 minutes to take it. So please make sure you have your notes out, your calculators out, and you're ready to go at the starting time. You'll be able to access the review this weekend online. You may make one note card for the test, however, it may not include the unit circle or trig charts values on them. You are expected to know them. Cards will be checked, and if they have these on them, will be confiscated. Grades should be updated to Brightspace by Sunday evening. That's the plan. Your current grade in MyMathLab is not your permanent or actual grade. It just gives you an idea of what you are earning in MyMathLab based on your work that you're putting into MyMathLab. It does give you zeros for incomplete or not started assignments. So if you're wondering like, oh my gosh, I've done my work, but why is my grade so low? It's because if you haven't done all the problems, then it's calculating the rest of them as zeros. Okay. All right. Have a great weekend, and it was a good day.